What if the universe itself could be hacked? Not just a computer or a network, but the very fabric of space, time, the stage on which everything we know unfolds. This isn't the plot of a sci-fi blockbuster. It's a question that some of the brightest minds in theoretical physics are asking today. Scientists are exploring ideas that sound almost too incredible to be real, bending space-time like a piece of code, opening shortcuts across the cosmos, and even manipulating the flow of time itself. These aren't just wild dreams, they're serious theories with profound implications for how we understand reality. From wormholes that could connect distant points in the universe to quantum entanglement acting as a cosmic cheat code, the possibilities are as mind-blowing as they are real. And it all starts with a revolutionary idea from a familiar name, Albert Einstein. His work on relativity opened the door to these groundbreaking concepts, and now we're on the brink of uncovering how space-time might not just be something we live in, but something we could one day control. So let's dive into the cutting-edge science that could change everything we know about the universe. Wormholes have long captured the imagination of science fiction fans, often portrayed as cosmic tunnels that let travelers zip across galaxies or leap through time in an instant. But what if these fantastical shortcuts aren't just the stuff of fiction? The idea of wormholes actually has its roots in real science, dating back to the groundbreaking work of Albert Einstein and physicist Rosen. Together, they proposed what's now known as the Einstein-Rosen bridge, a theoretical solution to the equations of general relativity. These bridges suggest that space-time could fold in on itself, creating a connection between two distant points in the universe. It's like taking a piece of paper, folding it so too far apart dots touch, and poking a hole through them. Suddenly, the journey between those points becomes almost instantaneous. But here's where things get even more intriguing. While Einstein and Rosen laid the groundwork, it was physicists like Kip Thorne who took the idea further, exploring whether wormholes could actually exist in our universe. Thorne proposed that these structures might be stabilized using something called exotic matter, a hypothetical substance with negative energy. This exotic matter could counteract the natural tendency of wormholes to collapse, keeping them open long enough for something or someone to pass through. The implications are staggering. If wormholes could be stabilized, they might allow us to traverse unimaginable distances in moments or even create pathways through time itself. Yet, as tantalizing as this idea is, it raises a big question. Are wormholes the only way to manipulate space-time? Could there be other, perhaps even more bizarre, methods to bend the fabric of the universe to our will? As we dive deeper into the mysteries of space-time, this question takes us to the next frontier of scientific exploration, one where the rules of physics as we know them might just be the beginning. Now, let's shift our focus to another groundbreaking idea that's reshaping our understanding of the universe: quantum entanglement. This bizarre phenomenon occurs when two particles become deeply linked, no matter how far apart they are in space. If you change one, the other instantly responds even if they're light years apart. It's as if they're communicating faster than the speed of light, seemingly breaking the rules of space-time as we know it. But what if this strange connection isn't just a quirk of quantum mechanics? What if it's actually tied to the very fabric of space-time itself? This is where physicists like Juan Maldacena and Leonard Susskind come in. They've proposed a revolutionary idea that quantum entanglement might be the glue holding space-time together. At first glance, this seems like science fiction, but their work points to something extraordinary. They've introduced the AR=EPR conjecture, a concept that bridges two seemingly unrelated ideas, wormholes and entangled particles. The conjecture suggests that these two phenomena are actually two sides of the same cosmic coin. In other words, when particles are entangled, there might be a hidden wormhole, a shortcut through space-time connecting them. Think of it like this. Imagine you and a friend are holding opposite ends of a very long rope. No matter how far apart you are, the rope keeps you connected. Now, replace the rope with a wormhole, and you've got a rough analogy for how entangled particles might be linked through space-time. This isn't just a neat metaphor, it's a potential window into how quantum mechanics could allow us to manipulate the very structure of reality. If we could harness entanglement, could we create shortcuts through space-time? Could we hack the universe itself? But here's where things get even more fascinating. This theory doesn't just stop at entangled particles and wormholes. It also ties into one of the most mysterious objects in the cosmos, black holes. These cosmic giants, with their immense gravitational pull, might hold the key to understanding how space-time and quantum mechanics intertwine. So, as we dive deeper into this cosmic puzzle, let's turn our attention to these enigmatic objects and the role they play in this grand theory. Black holes are more than just cosmic vacuum cleaners. They're some of the most fascinating natural laboratories in the universe. These mysterious objects, with their unimaginably strong gravitational fields, don't just pull in matter and light. They warp the very fabric of space-time itself. Near the event horizon, the boundary around a black hole from which nothing can escape, the rules of physics start to behave in ways that challenge everything we think we know. Time slows down, space bends, and the laws governing reality seem to unravel. It's in these extreme environments that scientists like Stephen Hawking saw an opportunity to explore the deepest mysteries of space-time. Hawking's groundbreaking work on black hole radiation, now famously known as Hawking radiation, revealed something extraordinary. Even black holes, which were once thought to be completely dark and impenetrable, emit faint streams of particles. This phenomenon suggests that black holes aren't just static objects, they're dynamic, interacting with the quantum realm in ways we're only beginning to understand. Hawking's discovery hinted that space-time might have a quantum structure woven together by tiny, fundamental threads that we can't yet see. It's as if black holes are whispering secrets about the quantum nature of reality itself. But what if these cosmic anomalies could do more than just reveal the quantum fabric of space-time? What if they could also show us how to manipulate it? Some scientists speculate that black holes might hold the key to understanding how space-time could be hacked. If we could decode the extreme distortions they create, we might unlock new ways to bend or even reshape space-time, opening the door to possibilities like faster-than-light travel or wormholes. Of course, these ideas are still firmly in the realm of theory, but they're rooted in the very real physics of black holes and their mind-bending effects on the universe. This leads us to an even more provocative idea, the holographic universe. Some researchers believe that the information about everything that falls into a black hole is somehow encoded on its surface like a cosmic hologram. If true, this could mean that space-time itself is a kind of projection, a lower-dimensional representation of a deeper, more complex reality. The connection between black holes and this holographic principle is still being explored, but it's a tantalizing clue that the universe might be far stranger and more interconnected than we ever imagined. And as we peel back these layers, we might just find the tools to rewrite the rules of space and time. Could the universe be like a hologram? It might sound like science fiction, but according to the holographic principle, this could be a fundamental truth about reality. Proposed by physicists Gerard T. Hooft and Leonard Susskind, this radical idea suggests that all the information within a volume of space, everything we see, touch, and experience, could be encoded on the boundary of that space, much like a hologram. Imagine a movie projected onto a flat screen, yet somehow containing the full depth and detail of a three-dimensional world. That's the essence of the holographic principle, and it turns our traditional understanding of space-time completely on its head. Instead of viewing space-time as a three-dimensional fabric, this theory implies that what we perceive as three dimensions might just be a projection of information stored on a two-dimensional surface. Think of it like a cosmic version of a video game, where the immersive 3D world you explore is actually built from code written on a flat 2D surface. In this framework, space-time itself might not be fundamental. Instead, it could emerge from deeper quantum processes like pixels forming an image on a screen. This idea opens up mind-bending possibilities. If space-time is not the bedrock of reality, but rather something that emerges from quantum information, could we manipulate that information to hack the very fabric of the universe? For instance, if we could somehow access and alter the data encoded on the holographic boundary, we might be able to bend space-time, create wormholes, or even travel through time. It's a tantalizing thought, and it suggests that the key to hacking space-time might lie in understanding and controlling the quantum code of reality. But here's the real kicker. If space-time is emergent, what does that mean for time itself? Could time, like space, be something we can manipulate? This leads us to an even more profound question. Is time truly linear, or is it just another layer of the hologram waiting to be decoded? Time dilation is one of those mind-bending ideas that sounds like science fiction but is firmly rooted in real science, thanks to Einstein's theory of relativity. At its core, time dilation tells us that time isn't a constant. It can stretch or compress depending on two key factors, gravity and velocity. For example, if you were to hang out near the edge of a black hole where gravity is insanely strong, time would crawl compared to someone far away in a weaker gravitational field. Or if you were traveling at nearly the speed of light, time would slow down for you relative to someone standing still. This isn't just theoretical, we've actually observed it. Atomic clocks on fast-moving jets or satellites in orbit tick slightly slower than those on Earth. It's a small effect in our everyday lives, but when you scale it up to cosmic extremes, the implications are staggering. Now, imagine what could happen if we pushed this phenomenon to its limits. Near a black hole, time dilation becomes so extreme that minutes for an observer could equal years or even centuries for someone far away. This raises an intriguing question. Could we harness this effect to manipulate time itself? Some scientists speculate that advanced civilizations might one day use time dilation as a tool, a form of temporal engineering. Picture this, a society so advanced that they could create artificial environments with extreme gravitational fields, or build spacecraft capable of reaching near light speeds, effectively creating time machines. They might slow down time to preserve resources, extend lifespans, or even send messages across vast stretches of the universe without the delays we experience today. But hacking time isn't just about slowing it down. What if we could reverse it or loop it? These ideas might sound wild, but they're grounded in the same principles that make time dilation possible. And here's where things get even more fascinating. Quantum mechanics might hold the key to unlocking these possibilities. Tiny particles like electrons don't play by the same rules as larger objects. They can exist in multiple states at once, teleport across distances, and even influence each other instantaneously, no matter how far apart they are. If we could somehow harness these quantum quirks, we might find a way to manipulate time on a scale that Einstein's relativity alone can't explain. This isn't just about building a time machine, it's about rethinking the very fabric of reality and asking whether time itself is something we can engineer. So, as we venture deeper into the mysteries of time dilation and temporal engineering, it's worth considering how quantum mechanics might offer the tools we need to take these ideas from theory to reality. What if the quantum realm is the missing piece of the puzzle, the gateway to bending time to our will? quantum tunneling is one of the most bizarre and fascinating phenomena in the quantum world. Picture this: a particle, like an electron, encounters a barrier that it doesn't have enough energy to overcome according to the rules of classical physics. Yet somehow it appears on the other side as if it simply passed through the barrier. This isn't magic, it's quantum mechanics at work. At the subatomic level, particles don't behave like solid objects. Instead, they exist as probabilities, and there's always a small chance they can tunnel through barriers that should be impenetrable. Now, here's where things get even more mind-bending. Some scientists theorize that this quantum tunneling effect could hold the key to manipulating space-time itself. Imagine if we could harness this process to create shortcuts through the fabric of the universe. Instead of traveling vast distances through space, particles, or even larger objects could potentially bypass those distances by tunneling through the barriers of space-time. This could open up possibilities for faster-than-light travel or even altering the flow of time itself. On a microscopic scale, quantum tunneling already happens naturally, but what if we could scale it up? Could we one day engineer systems that exploit this phenomenon to manipulate space-time on a macroscopic level? Some researchers believe that understanding and controlling quantum tunneling could be the first step toward creating real-world applications like wormholes or time-bending devices. It's a wild idea, but the quantum world has already shown us that reality is far stranger than we once thought. As we dive deeper into these theories, the next question becomes, how do these quantum effects, which operate on such tiny scales, translate to the larger universe we live in? Could the same principles that allow particles to tunnel through barriers also allow us to manipulate space-time on a grander scale? The answers might lie in the mysterious interplay between quantum mechanics and the cosmic structure of the universe itself. Now, let's dive into one of the most fascinating phenomena in quantum physics, the Casimir effect. Picture two uncharged metal plates placed incredibly close together in a vacuum. At this microscopic scale, something strange happens. The plates are drawn toward each other by an invisible force. This isn't magic, it's the result of quantum fluctuations, the constant bubbling of particles and antiparticles that pop in and out of existence in the fabric of space-time. The Casimir effect demonstrates that even in the absence of traditional forces, the quantum world can produce measurable, real-world effects. But here's where it gets even more intriguing. This effect is closely tied to the idea of negative energy, a concept that sounds like science fiction but is grounded in real physics. Negative energy isn't just the absence of energy, it's a theoretical form of energy that could have bizarre properties, like the ability to stabilize wormholes or even warp space-time itself. Imagine a region of space where the energy density is lower than that of empty space. This negative energy could, in theory, counteract the immense gravitational forces that would otherwise collapse a wormhole or make warp travel impossible. Physicists like Harold White have taken this idea even further. White, known for his work on advanced propulsion systems at NASA, has explored how the Casimir effect and negative energy could be harnessed to create a warp drive. The idea isn't just to travel faster than light, but to bend space-time itself, creating a warp bubble that moves through the universe while the ship inside remains stationary. It's a concept that sounds straight out of Star Trek, but it's rooted in the math of general relativity and the strange behavior of quantum mechanics. So, how does this all connect? The Casimir effect gives us a glimpse into how quantum phenomena could manipulate space-time on a fundamental level. It's a tantalizing hint that the universe might allow for shortcuts or distortions that could revolutionize how we think about travel, energy, and even the nature of reality itself. And as we explore these possibilities, the concept of a warp bubble becomes more than just a theoretical curiosity. it's a potential gateway to understanding how we might one day hack the very fabric of space-time. Now let's shift our focus to one of the most fascinating ideas in theoretical physics: warp drives. You've probably seen them in science fiction, but what if I told you there's a real scientific foundation behind this concept? Enter Miguel Alcubierre, a physicist who proposed a theoretical model in the 1990s that could, in theory, allow faster-than-light travel without breaking Einstein's laws of relativity. It sounds like something straight out of Star Trek, but the math checks out, at least on paper. Here's how it works. Imagine space-time as a rubber sheet. A warp drive would essentially contract the space in front of a spacecraft while expanding the space behind it. This creates a kind of bubble that moves through space-time, carrying the ship along with it. Inside this bubble, the spacecraft itself isn't moving faster than light. It's the space around it that's being manipulated. Think of it like riding a wave. You're not propelling yourself forward, but the wave is carrying you. This way, the speed of light limit isn't violated because the ship isn't technically traveling through space. It's being carried by the warped space itself. But of course, there's a catch. To create this warp bubble, you'd need something called negative energy, a type of energy that, as the name suggests, has a negative value. This isn't just rare, it's something we've never observed in nature. Some theories suggest that exotic matter or quantum field effects might produce it, but we're still far from understanding how to harness it. And even if we could, the amount of energy required would be staggering, possibly more than all the energy in the observable universe. So while the Alcubierre metric is mathematically sound, turning it into a practical technology feels like a distant dream. Still, the idea of hacking space-time to enable interstellar travel is tantalizing. What if one day we could generate enough negative energy or find a way to manipulate space-time more efficiently? Could warp drives become a reality, or are they destined to remain in the realm of theory and fiction? This brings us to the next big question. What other possibilities might exist for bending the rules of space and time? What if the key to hacking space-time lies not in building massive machines or launching rockets, but in harnessing the strange power of quantum computers? This leads us to the ninth theory, the idea that quantum computers could one day simulate the fabric of space-time itself. Imagine a virtual environment where we could test theories about bending, twisting, or even rewriting the rules of space-time, all without leaving the lab. It sounds like science fiction, but this is a very real possibility being explored by leading physicists and computer scientists. Quantum computers operate on principles that are fundamentally different from classical computers. Instead of processing information in binary bits, zeros and ones, they use quantum bits or qubits, which can exist in multiple states at once. This allows them to perform calculations at speeds that are unimaginable with today's technology. But here's where it gets even more fascinating. Because space-time itself may have a quantum foundation, quantum computers could be uniquely suited to simulate it. By creating these simulations, scientists could explore how space-time behaves under conditions that are impossible to replicate in the real world, like near a black hole or during the Big Bang. These simulations wouldn't just be academic exercises, they could provide practical insights into how we might manipulate space-time. For example, if we discover that certain quantum states can create ripples in space-time, we might one day use this knowledge to build devices that can warp space or even create artificial wormholes. It's a mind-bending idea, but it's rooted in the growing understanding that space-time isn't a fixed, unchanging backdrop. It's a dynamic, malleable entity that responds to quantum interactions. This theory also bridges the gap between quantum computing and theoretical physics, two fields that are increasingly intertwined. As quantum computers become more powerful, They could help us solve some of the biggest mysteries in physics, like the nature of dark matter, the unification of quantum mechanics and gravity, and even the possibility of multiple dimensions. Each simulation could bring us closer to understanding the true nature of reality and how we might one day control it. Now, all of this raises an intriguing question. If we can simulate space-time so accurately, could it mean that our own universe is a simulation? The idea of a simulated universe has been debated for decades, but quantum computing adds a new layer to the discussion. If we're able to create such detailed simulations, it's not hard to imagine that a more advanced civilization might have already done the same, and that we could be living inside one of their creations. This connection between quantum simulations and the nature of reality itself is a fascinating frontier, and it's one we'll explore further as we dive into the next theory. What if everything we know, every star, every galaxy, even the fabric of space-time itself, is nothing more than lines of code in a cosmic computer program? This is the essence of the simulation hypothesis, a theory that has captivated scientists, philosophers, and even tech billionaires. Proposed by philosopher Nick Bostrom, the simulation hypothesis suggests that our universe might be an artificial construct, a simulation created by an advanced civilization far beyond our understanding. And if that's the case, then space-time, the very stage on which the drama of the cosmos plays out, could be nothing more than a programmed framework, one that might be altered, tweaked, or even hacked. Think about it. If space-time is a construct within a simulation, it would operate under rules set by the programmers. These rules could include the speed of light, the behavior of gravity, and even the way time flows. But here's where it gets fascinating. If those rules are programmable, they might also be reprogrammable. Imagine the implications: manipulating time, bending space, or even creating entirely new dimensions, all by accessing the underlying code of the simulation. It's a mind-bending possibility, one that blurs the line between science and science fiction. But how realistic is this idea? While we don't have direct evidence that we're living in a simulation, some scientists argue that the sheer complexity of our universe, from the precise constants of physics to the intricate patterns of nature, could be seen as clues pointing toward a designed reality. And if that's true, then the question becomes, who's at the controls? Could we, as conscious beings within the simulation, ever gain access to the source code and manipulate space-time to our advantage? This leads us to another intriguing layer, the multiverse. If our universe is a simulation, could there be other simulations running alongside it, each with its own set of rules and realities? The multiverse theory suggests that multiple universes could exist parallel to ours, each with different physical laws. In the context of the simulation hypothesis, this could mean that our universe is just one of countless simulations, each created by different civilizations for different purposes. The idea of hacking space-time suddenly becomes even more complex and more tantalizing. What if crossing into another simulated universe is as simple as rewriting a few lines of code? The possibilities are as limitless as they are speculative. While the simulation hypothesis remains a theory, one that's impossible to prove or disprove with our current understanding, it opens up a world of questions about the nature of reality and our place within it. It challenges us to think beyond the boundaries of what we know and consider that the universe might not be as fixed or immutable as it seems. And if space-time is indeed a construct, then the next great frontier of exploration might not be the stars, but the very code that makes them shine. What if our universe isn't the only one? What if space-time, as we know it, is just one thread in an infinite tapestry of realities? This is the mind-bending idea behind the multiverse theory, a concept that suggests our universe is just one of countless parallel worlds, each with its own unique version of space and time. Imagine an endless array of universes, each slightly different from the next, where every possible outcome of every event exists somewhere. It's a theory that not only stretches the boundaries of our imagination, but also challenges our understanding of reality itself. The foundations of the multiverse idea are rooted in quantum mechanics and string theory. In quantum mechanics, every decision or event creates a branching path leading to multiple possible outcomes. Some scientists suggest that these branches aren't just hypothetical, they're real, existing as separate universes. Meanwhile, string theory proposes that our universe is just one of many brains floating in a higher dimensional space, each representing a different universe. Together, these theories paint a picture of a cosmos far more vast and complex than we ever imagined. But what does this mean for hacking space-time? If the multiverse exists, then space-time isn't a singular, fixed structure. It's one of countless configurations. Manipulating it might involve more than just bending or warping the fabric of our reality. It could mean accessing or even merging with parallel universes. Think of it like tuning into a different frequency on a cosmic radio. If we could find a way to switch channels, we might unlock entirely new dimensions of space and time, opening doors to realities we can barely comprehend. Of course, the idea of accessing parallel universes raises more questions than answers. How would we even begin to interact with another universe? Could we travel between them, or would the laws of physics in those realities make it impossible? And if we did manage to manipulate these connections, what kind of consequences might that have for our own universe? These are the kinds of questions that keep scientists and theorists up at night, pushing the boundaries of what we think is possible. This brings us to another fascinating concept: cosmic strings. These hypothetical, thread-like structures are thought to stretch across the universe, remnants of the early moments after the Big Bang. Some theories suggest that cosmic strings could act as bridges between different universes, potentially offering a way to navigate the multiverse. If they exist, they might hold the key to understanding and even hacking the connections between parallel space-times. The multiverse theory doesn't just challenge our understanding of reality, it redefines it. It suggests that space-time isn't a singular, unchanging entity, but a dynamic, multifaceted structure intertwined with countless other realities. And while the idea of accessing these parallel worlds might seem like science fiction, it's a possibility that scientists are actively exploring, blurring the line between what we know and what we've yet to discover. What if the universe itself holds the keys to unlocking the mysteries of space-time, hidden in the very fabric of existence? Enter cosmic strings, hypothetical one-dimensional defects that may have formed in the early universe. These aren't physical strings like the ones you'd find on a guitar, but rather flaws or cracks in the structure of space-time itself, remnants of the intense energy fluctuations that occurred moments after the Big Bang. Picture them as cosmic scars stretching across unimaginable distances, thinner than an atom but with immense gravitational influence. If cosmic strings exist, they could be one of the most fascinating tools for space-time manipulation. Their extreme density and tension would warp the space-time around them, creating gravitational effects so intense that they could theoretically bend light or even time itself. Some scientists have speculated that if two cosmic strings were to interact or collide, they might create closed loops of space-time, potentially opening up shortcuts or wormholes across the cosmos. Imagine a highway system built not by humans but by the universe itself, allowing us to travel vast distances in the blink of an eye. But how could we harness such a phenomenon? Cosmic strings, if detected, might offer a way to test the limits of space-time engineering. By studying their behavior and interactions, we could uncover new ways to manipulate gravity or create stable pathways through space. It's a tantalizing idea, using the universe's own architecture to hack space-time. Yet, cosmic strings remain elusive, their existence still theoretical. Their detection would not only confirm a key prediction of modern physics, but also open the door to revolutionary possibilities for space travel and energy manipulation. These cosmic threads also hint at a deeper connection to the forces shaping our universe. As we explore their potential, we're led to another profound mystery: dark energy. Could cosmic strings and dark energy be intertwined, two sides of the same cosmic coin? Dark energy, the mysterious force driving the accelerated expansion of the universe, might hold clues about how space-time itself evolves. Understanding one could shed light on the other, unraveling the secrets of the cosmos one thread at a time. Now, let's shift our focus to one of the most enigmatic forces in the universe: dark energy. This invisible, pervasive energy is believed to be the driving force behind the accelerated expansion of the cosmos. Unlike gravity, which pulls things together, dark energy seems to push space itself apart, stretching the very fabric of space-time. But what exactly is dark energy, and why does it hold such profound implications for our understanding of the universe? Scientists estimate that dark energy makes up roughly 68% of the universe, yet its true nature remains shrouded in mystery. Some theories suggest it could be a property of space itself, a kind of cosmic pressure that emerges from the vacuum of empty space. Others propose it might be tied to an unknown field or particle that permeates the cosmos. What's fascinating is that this mysterious force doesn't just shape the universe on a grand scale. It could also hold the key to understanding and potentially manipulating space-time itself. Imagine if we could tap into dark energy's power. If it's capable of stretching space-time, could we one day harness it to create warp fields or even stabilize wormholes? While this sounds like science fiction, the idea isn't entirely out of reach. Some researchers speculate that by deepening our understanding of dark energy, we might uncover new ways to control the geometry of space-time, opening the door to technologies that could revolutionize space travel and our perception of reality. But here's the kicker: dark energy doesn't just challenge our understanding of space, it also has profound implications for time. As the universe expands, the flow of time itself is influenced by the stretching of space. This interplay between space and time suggests that mastering dark energy could give us unprecedented control over both dimensions. It's a tantalizing possibility that bridges the gap between cosmology and the cutting-edge field of time crystals, where the very structure of time can be manipulated in surprising ways. Speaking of time crystals, this brings us to another fascinating concept, one that ties dark energy's cosmic influence to the quantum realm. Could the same principles that govern dark energy's expansion of space-time also apply to the creation of time crystals, structures that defy the conventional flow of time? Let's explore this intriguing connection next. Now, let's step into the fascinating world of time crystals, a concept that sounds like it's straight out of science fiction, but is very much grounded in cutting-edge physics. First proposed by Nobel laureate Frank Wilczek, time crystals are a new phase of matter that defies our everyday understanding of how objects behave. Unlike ordinary crystals, which have a repeating structure in space, time crystals exhibit a repeating pattern in time. Imagine a clock that ticks forever without any energy input. This is the strange, almost magical behavior of time crystals in their ground state, the lowest energy state of a system. It's as if time itself has become a playground for these structures where motion persists indefinitely, unchanging and unyielding. But how does this connect to the idea of hacking time? Well, time crystals challenge one of the most fundamental principles of physics, the idea that perpetual motion is impossible. By existing in a state of continuous, self-sustaining oscillation, they hint at a deeper layer of reality where time might not flow as we perceive it. Scientists are exploring whether these quantum materials could act as a kind of time machine at the microscopic level, allowing us to manipulate temporal processes in ways we've never thought possible. For instance, could we use time crystals to create quantum clocks that operate with unprecedented precision? Or even more intriguingly, could they be the key to encoding information in time itself, opening up new possibilities for quantum computing and communication? This leads us to an even bigger question. How do these ideas fit into the broader puzzle of quantum gravity? Time crystals exist at the intersection of quantum mechanics and the nature of time, a realm where gravity, as described by Einstein's theory of relativity, still resists unification with quantum theory. By studying how time crystals manipulate temporal structures, scientists hope to uncover clues about how time behaves at the smallest scales where quantum effects dominate. Could time crystals be a stepping stone toward understanding the fabric of space-time itself? The connection is tantalizing, and it's one of the many reasons why this field of research is sparking so much excitement. As we push the boundaries of what we know, time crystals remind us that the universe is far stranger and more wondrous than we often give it credit for. They challenge our assumptions, inspire new questions, and might just hold the key to unlocking some of the deepest mysteries of time itself. And speaking of mysteries, the next theory we'll explore takes us even further into the unknown, into the realm of quantum gravity and how it might reshape our understanding of space-time entirely. One of the most profound challenges in modern physics is the search for a theory of quantum gravity, a framework that could finally unite Einstein's theory of general relativity with the strange, probabilistic world of quantum mechanics. These two pillars of physics have been wildly successful in their own domains, but they seem to clash when we try to apply them together, especially in extreme environments like black holes or the moments just after the Big Bang. This quest isn't just about solving equations, it's about uncovering the true nature of space-time itself. What if the fabric of the universe isn't as smooth and continuous as we've always imagined? What if, at the tiniest scales, space-time is woven together by something far more intricate and dynamic? Quantum gravity theories, like string theory or loop quantum gravity, suggest that space-time might be emergent, a structure that arises from more fundamental building blocks such as quantum fields or discrete loops. This means that what we perceive as the smooth, unbroken fabric of the cosmos could actually be a kind of illusion, like the surface of a pond that looks still but is made up of countless ripples and vibrations. If this is true, then space-time itself might be something we could, in principle, manipulate not with massive cosmic forces, but by tweaking those underlying quantum elements. Imagine if, at the quantum level, space-time behaves more like a network or a lattice with connections that can be reconfigured. In that case, hacking space-time might not require bending the universe with massive objects or energy, but instead finding ways to influence those quantum threads. Some scientists speculate that advanced civilizations, or even future humans, might one day develop technologies to do just that, potentially enabling shortcuts through space or even the creation of entirely new regions of the cosmos. But here's where things get even more fascinating. If space-time is emergent, then the very idea of hacking it might not just be about changing its shape or structure. It could also mean rewriting the rules that govern it. This leads us to the next big question. Could space-time itself be a kind of code, a set of instructions that can be reprogrammed? As we explore these ideas, we're not just pushing the boundaries of physics, we're reimagining what the universe might be capable of. And that brings us to the concept of emergent space-time, where the fabric of reality itself is a dynamic, evolving system waiting to be understood and perhaps one day mastered. So, if space-time isn't fundamental, if it's not the bedrock of reality but something that emerges from deeper quantum processes, what does that mean for our understanding of the universe? This is where the idea of emergent space-time comes into play. Think of it like this. Imagine watching a movie on a screen. The characters, the scenes, the entire story, they all emerge from the pixels on that screen. But if you zoom in close enough, you'll see that the image isn't the fundamental layer. It's built from something smaller, something more basic. In the same way, space-time might not be the ultimate foundation of reality. Instead, it could be a kind of projection or illusion, arising from the intricate interactions of quantum bits, tiny, fundamental building blocks we're only beginning to understand. This idea isn't just speculative, it's supported by theories like the holographic principle. According to this principle, the information needed to describe everything within a volume of space can actually be encoded on its boundary, like a two-dimensional surface holding all the data for a three-dimensional world. It's as if the universe is a hologram, with space-time being the image we perceive, while the real code exists on a lower dimensional plane. If this is true, it opens up fascinating possibilities. If space-time is emergent, then it's not fixed or immutable. It's more like a dynamic system, something that could, in theory, be reprogrammed. Now, let's take that a step further. If space-time is a construct based on quantum processes, could we hack it? Could we manipulate the underlying quantum mechanics to alter the fabric of reality itself? Some scientists believe it's not entirely out of the question. If we could decode the quantum rules governing space-time, we might one day find ways to tweak them, perhaps bending time, warping space, or even creating entirely new structures within the universe. It's a concept that feels straight out of science fiction, but it's rooted in cutting-edge physics. And here's where things get even more intriguing. This idea of emergent space-time ties directly into information theory. Information, after all, is at the heart of the holographic principle. If space-time is built from quantum information, then understanding how that information flows, interacts, and organizes itself could be the key to unlocking its secrets. It's not just about space and time as we experience them, it's about the data, the patterns, the code that makes them what they are. As we explore this connection further, we'll see how information theory might hold the answers to some of the most profound questions about the nature of reality. But for now, let's sit with this thought. If space-time is a construct, then the universe might be far more malleable and far more mysterious than we ever imagined. Now, let's shift our focus to a theory that bridges the gap between the physical universe and the digital realm: information theory and space-time. What if the fabric of reality itself isn't just made of matter and energy, but of information? This idea, rooted in groundbreaking concepts like black hole thermodynamics and the holographic principle, suggests that space-time might be a kind of cosmic data structure. Imagine the universe as a vast, interconnected network where every particle, every force, and even the flow of time is encoded in bits of information. It's a mind-bending perspective, but one that's gaining traction among leading physicists. The holographic principle, for instance, proposes that all the information contained within a volume of space can be represented as a two-dimensional surface, like a hologram. This means that the three-dimensional world we experience could be a projection of information stored on a distant boundary. Black holes, often seen as the ultimate mystery of space-time, play a key role here. According to Stephen Hawking's work, black holes emit radiation and slowly lose information, a process that challenges our understanding of how information interacts with space-time. If information can escape a black hole, could it also be manipulated to reshape the very fabric of reality? This leads us to an even more tantalizing possibility: hacking space-time itself. If space-time is fundamentally about information, then manipulating that information could allow us to alter the geometry of the universe or even control the flow of time. Think of it like rewriting the code of a simulation. By tweaking the underlying data, we might one day create new geometries, bend space-time in ways that defy classical physics, or even slow down or speed up time. These aren't just sci-fi dreams, they're ideas being explored at the cutting edge of theoretical physics and information science. But how does this connect to the world of quantum field theory? At its core, quantum field theory describes how particles and forces interact within the framework of space and time. If space-time is an information-based structure, then quantum fields might be the language in which that information is written. This merging of ideas where physics meets information science opens up entirely new ways to think about the universe. It's a reminder that the boundaries between disciplines are often where the most exciting discoveries happen. So, as we dive deeper into the quantum realm, let's explore how these theories might reshape our understanding of reality itself. Let's dive into the 18th theory, quantum field theory, and its fascinating relationship with space-time. At its core, quantum field theory describes the universe not as a collection of discrete particles, but as a vast, interconnected web of fields. Think of these fields as invisible blankets stretching across all of space and time. Particles like electrons or photons aren't just tiny dots floating around their ripples or excitations in these underlying fields. This means everything we see, from the light we perceive to the matter we touch, is essentially a vibration in the fabric of these quantum fields. Now here's where things get really intriguing. If space-time itself is woven into this tapestry of fields, could we manipulate it by altering those fields? Some scientists believe that hacking space-time might involve precisely that, finding ways to control or reshape these quantum fields. Imagine being able to tweak the very fabric of reality, not just by moving objects through space, but by changing the rules of space and time themselves. This isn't just science fiction, it's a real possibility being explored at the cutting edge of theoretical physics. But how far could we take this idea? If we could interact with these fields, could we create shortcuts through space-time or even warp it to our advantage? The answers might lie in understanding how these quantum fields are tied to the structure of space-time. And that brings us to another mind-bending concept: extra dimensions. Could the key to manipulating space-time be hidden in dimensions beyond the three we experience every day? Let's explore that next. But what if space-time isn't as straightforward as we think? What if there's more to it, dimensions we can't see or even fully comprehend? This is where the 19th theory takes us into the realm of extra dimensions, a concept that sounds like science fiction but is rooted in serious scientific exploration. Theories like string theory suggest that our universe might not just have the three spatial dimensions we're familiar with: up and down, left and right, forward and backward, but potentially many more hidden from our perception. These extra dimensions could be tightly curled up, so small that they're invisible to us, or they might exist on scales we simply can't detect with current technology. Imagine space-time as a sheet of paper. We see it as flat, two-dimensional, but if you could zoom in, you might find tiny folds or creases, hidden layers that exist beyond what we can perceive. In the same way, these extra dimensions could be folded into the fabric of our universe, offering new pathways for manipulating space-time itself. Some scientists theorize that by tapping into these higher dimensional spaces, we might unlock the ability to bend space-time in ways that seem impossible in our familiar three-dimensional world. Think of it as finding a secret shortcut through the cosmos, or even accessing parallel realities that exist alongside our own. The implications are staggering. If these extra dimensions are real, they could provide a playground for hacking space-time. For instance, higher dimensional physics might allow us to create stable wormholes, tunnels through space-time that could serve as cosmic highways between distant points in the universe. Or they could give rise to phenomena like quantum entanglement, where particles interact instantaneously across vast distances, seemingly bypassing the limitations of space and time as we know them. These ideas push the boundaries of what we consider possible, suggesting that the universe is far more complex and far more malleable than we've ever imagined. But how does this connect to the fabric of reality as a whole? To answer that, we need to turn our attention to another key piece of the puzzle: vacuum energy. This mysterious force, often referred to as the energy of empty space, might hold the key to understanding how these extra dimensions interact with our own. It's a bridge between the hidden layers of the universe and the space-time we experience every day, and it might just be the missing link in our quest to unlock the secrets of the cosmos. Vacuum energy might sound like something out of science fiction, but it's a very real concept in physics. It's the energy that exists in what we think of as empty space, a seething, invisible sea of quantum fluctuations. Even in a perfect vacuum, particles and their antimatter counterparts pop in and out of existence, creating tiny bursts of energy. This isn't just theoretical. It's been indirectly observed through phenomena like the Casimir effect, where two uncharged plates placed close together in a vacuum experience an inexplicable force pushing them together. That force, it's the result of vacuum energy at work. Now, imagine if we could tap into that energy. What might we achieve? Some scientists believe vacuum energy could be the key to manipulating space-time itself. Think about it. If we could control these quantum fluctuations, we might be able to bend the fabric of the universe. One tantalizing possibility is the creation of wormholes, shortcuts through space-time that could allow near instantaneous travel across vast distances. Another idea is the formation of warp bubbles, regions of space-time where the rules of physics are altered to enable faster-than-light travel. Sounds like something straight out of Star Trek, right? But here's the kicker: the math behind these ideas isn't just speculative. Theoretical frameworks like the Alcubierre drive suggest that such feats might be possible, at least in principle. But let's not get ahead of ourselves. Harnessing vacuum energy comes with monumental challenges. For one, the energy densities involved are staggering, far beyond anything we can currently generate or control. And even if we could access that energy, stabilizing it to create something like a wormhole or warp bubble would require technology that feels almost unimaginable today. There's also the question of unintended consequences. Manipulating space-time on such a scale could have unpredictable effects, potentially destabilizing the very fabric of reality as we know it. Still, the possibilities are too exciting to ignore. What if vacuum energy could be the bridge between quantum mechanics and general relativity, two pillars of physics that have yet to be fully unified? This is where things get even more intriguing. The same principles that make vacuum energy a potential tool for space-time manipulation also tie into the concept of quantum teleportation, a process that allows particles to transfer information instantly across vast distances, seemingly defying the speed of light. But that's a story for the next section, where we'll explore how these quantum phenomena could revolutionize our understanding of the universe. What if the key to hacking space-time lies not in massive starships or wormholes, but in the tiniest building blocks of the universe? Enter quantum teleportation, a phenomenon so strange that it feels like it's straight out of science fiction. At its core, quantum teleportation relies on something called entanglement, where two particles become so deeply connected that no matter how far apart they are, changing the state of one instantly affects the other. This isn't just a quirky lab trick. It's a real-world example of how information can be transferred across vast distances faster than the speed of light, seemingly breaking one of the universe's most fundamental rules. But here's where it gets mind-blowing. If we can harness this phenomenon, could we use it to manipulate space-time itself? Imagine sending information, or even matter, from one point in the universe to another without traveling through the space in between. It's not just about communication. This could open the door to entirely new ways of moving through the cosmos. Scientists are already exploring how quantum teleportation might allow us to bypass the limitations of light speed, potentially unlocking faster than light travel or even creating shortcuts through space-time. The implications are staggering. If we can master this process, we might be able to send data or even physical objects across the galaxy in the blink of an eye. But it's not just about speed. Quantum teleportation could also give us a new lens to examine the very fabric of reality. By studying how entangled particles interact with space-time, we might uncover secrets about how the universe stitches together the dimensions we experience every day. And this is where things get even more intriguing. Quantum teleportation doesn't just challenge our understanding of space, it also raises questions about time. Could entangled particles be used to create connections not just across space, but across time itself? Some theorists speculate that this could lead to the creation of time loops, where information or matter is sent back to an earlier moment, creating a feedback loop that defies our linear experience of time. It's a wild idea, but one that's grounded in the strange, counterintuitive principles of quantum mechanics. So, what does this all mean for the future of space-time manipulation? Quantum teleportation offers a tantalizing glimpse into how we might one day bend the rules of the universe to our will. But as we'll see next, the connection between these ideas and the concept of time loops might just take us even further down the rabbit hole of theoretical physics. Now, let's step into the mind-bending world of closed time-like curves, or CTCs for short. These are hypothetical pathways through space-time that loop back on themselves, creating the possibility of traveling into the past. Imagine drawing a line on a piece of paper, only to have that line curve around and reconnect with its starting point. That's essentially what a closed time-like curve does, except instead of paper, it's the fabric of the universe itself. If such curves exist, they could allow for time travel, but not without raising some serious questions about the nature of reality. Think about it. If you could travel back in time along one of these curves, what stops you from altering events that have already happened? This is where the idea of temporal paradoxes comes into play. The classic example is the grandfather paradox, where someone travels back in time and prevents their own birth. But closed time-like curves don't just open the door to paradoxes, they also challenge our understanding of cause and effect. In a universe where time loops exist, does the past truly dictate the future, or could the future somehow influence the past? Some scientists, like Nobel laureate Kip Thorne, have explored the theoretical foundations of CTCs, suggesting that they might exist in extreme environments, such as near-rotating black holes or within wormholes. These structures could act as shortcuts through space-time, bending it so severely that time itself folds back on itself. But while the math might allow for such possibilities, the practical implications are staggering. Could we harness these curves to rewrite history? Or would the universe enforce some kind of cosmic rulebook to prevent paradoxes? And here's where things get even more intriguing. The existence of closed time-like curves ties directly into the concept of quantum foam, a turbulent, frothy structure that some physicists believe underlies the very fabric of space-time at the smallest scales. If space-time isn't smooth but instead resembles a bubbling foam, could these tiny, chaotic fluctuations be the key to unlocking time loops? It's a question that bridges the gap between the strange world of quantum mechanics and the mind-bending possibilities of time travel. Imagine zooming in on the fabric of the universe so close that space-time itself begins to look less like a smooth, continuous surface and more like a chaotic, bubbling sea. This is the bizarre realm of quantum foam, a concept that suggests at the tiniest scales imaginable, space-time isn't calm or orderly. Instead, it's a frothy, turbulent environment where tiny fluctuations constantly twist and warp the very structure of reality. Think of it like the surface of a boiling pot of water, but instead of bubbles, these are fluctuations in space and time itself. These fleeting distortions, though unimaginably small, could hold the key to understanding how we might one day manipulate the universe's most fundamental framework. So, what exactly is quantum foam? It's a theoretical structure that arises from the principles of quantum mechanics and general relativity. At scales so small they're measured in Planck lengths. That's 1/1,000,000th of a trillionth the size of an atom. Space-time isn't smooth. Instead, it's a seething, dynamic froth where particles and energy pop in and out of existence in a chaotic dance. These fluctuations aren't random noise, they're the result of the universe's inherent uncertainty at the quantum level. In this environment, the very concepts of distance and time become fuzzy, almost as if space-time itself is alive with activity. Now, here's where things get even more fascinating. If space-time is this turbulent at its core, could we somehow harness or control these quantum fluctuations? Some scientists speculate that manipulating quantum foam might be the key to hacking space-time itself. Imagine being able to stabilize or redirect these tiny distortions like smoothing out waves on the surface of a pond. If we could do that, we might unlock the ability to bend space-time in ways that seem straight out of science fiction. This isn't just about creating wormholes or time travel, though those ideas are certainly tantalizing. It's about fundamentally understanding how the universe works at its most basic level and using that knowledge to engineer space-time itself. This idea ties directly into the broader concept of space-time engineering, a field that explores how we might one day reshape the cosmos to suit our needs. By studying quantum foam, we're not just peering into the chaotic heart of space-time, we're also exploring the tools that could allow us to manipulate it. It's like discovering the gears and levers of reality hidden beneath the surface of what we see. And while this might sound like a distant dream, the theories are already laying the groundwork for what could become humanity's next great leap in understanding and perhaps even controlling the universe. What if the key to unlocking the secrets of the universe has already been discovered not by us, but by civilizations so advanced that their technology operates on a scale we can barely comprehend? This is the tantalizing idea behind the 24th theory, space-time engineering and advanced civilizations. Imagine beings who have transcended the limitations of physics as we know it, bending the fabric of space-time to their will. These hypothetical civilizations might not just travel through space-time, they could reshape it entirely, crafting wormholes for instantaneous travel, manipulating gravity to communicate across galaxies, or even birthing entirely new universes. The concept of space-time engineering hinges on the idea that space and time are not fixed, immutable structures but malleable dimensions that can be twisted, stretched, or folded. For a civilization with the right tools and knowledge, space-time could become a canvas and physics itself a set of brushstrokes. Think about it, if we can already manipulate light and sound with our current technology, what might a species millions or billions of years ahead of us achieve? They could use space-time as a medium for faster-than-light travel, creating shortcuts through the cosmos that defy our understanding of distance. Or perhaps they've developed ways to encode information within the fabric of space-time itself, turning the universe into a vast, interconnected network. But the possibilities don't stop there. Some scientists speculate that these advanced beings might even possess the ability to create new universes, essentially becoming cosmic architects. By manipulating the fundamental constants of physics, they could design universes with entirely different laws, perhaps even ones tailored to their own needs. This isn't just science fiction, it's a logical extension of what we know about quantum mechanics and general relativity, taken to its ultimate conclusion. As we ponder these mind-bending ideas, it's hard not to wonder, could humanity ever reach such a level of mastery over space-time? And if we did, what would stop us from hacking the very fabric of reality? This brings us to an intriguing connection, the concept of cosmic censorship. Proposed by physicist Roger Penrose, cosmic censorship suggests that the universe has built-in safeguards to prevent the kind of chaos that could arise from naked singularities, points where the laws of physics break down. If advanced civilizations are out there bending space-time to their will, could cosmic censorship be the universe's way of keeping their power in check? Or would they find a way to bypass even these cosmic rules? As we explore these questions, the line between science and speculation blurs, opening up a universe of possibilities. But what if the universe has its own set of rules to keep us from prying too deeply into its most mysterious corners? This is where the cosmic censorship conjecture comes into play. Proposed by physicist Roger Penrose, this idea suggests that singularities, those infinitely dense points at the heart of black holes, are always hidden from view, shielded by an event horizon. Essentially, the universe might be playing a game of cosmic hide and seek, keeping these extreme regions of space-time safely out of reach. Now, why does this matter when it comes to hacking space-time? Well, singularities are thought to be the ultimate test of our understanding of physics. They're where the laws of general relativity break down and where quantum mechanics might take over. If we could somehow access or manipulate a singularity, it could open the door to bending space-time in ways we can barely imagine. But cosmic censorship throws a wrench into that plan. If singularities are always hidden, then our ability to interact with them, and by extension to hack space-time, could be severely limited. This leads us to an intriguing question. Are singularities the key to unlocking space-time manipulation, or are they nature's way of saying, this far and no further? Some scientists believe that if we could ever find a way to bypass cosmic censorship, perhaps through advanced technology or new physics, we might uncover the secrets of space-time. Others argue that the conjecture is a fundamental law of the universe, a safeguard against chaos and unpredictability. Either way, the cosmic censorship conjecture forces us to confront the limits of what's possible in our quest to manipulate the fabric of reality. And here's where things get even more fascinating. These ideas about singularities and the boundaries of space-time manipulation start to blur the lines between physics and something far more abstract, the concept of quantum consciousness. Could the way we think about singularities hidden, yet potentially powerful, have parallels in the way our own minds process reality? As we dive deeper into the mysteries of space-time, we'll explore how these theories might connect to the enigmatic idea of quantum consciousness and what it could mean for our understanding of the universe and ourselves. What if the very fabric of space-time isn't just shaped by gravity or quantum particles, but by consciousness itself? This is the bold claim at the heart of the 26th theory we're exploring, quantum consciousness and space-time. It's a controversial idea, but one that has gained traction thanks to the work of renowned physicist Sir Roger Penrose and others. At its core, this theory suggests that the mysterious nature of consciousness might be deeply intertwined with the quantum processes that govern the universe. And if that's true, it opens up a mind-bending possibility. Hacking space-time could mean hacking the mind. Penrose, along with anesthesiologist Stuart Hamroff, proposed that consciousness arises from quantum processes occurring within the brain's neurons. They argue that these processes are connected to the fundamental structure of space-time, hinting at a universe where the mind and the cosmos are not separate entities but deeply linked. If consciousness operates on a quantum level, it might interact with the very fabric of reality in ways we're only beginning to understand. This raises a tantalizing question. Could manipulating consciousness through advanced technology or even deep meditation allow us to alter the structure of space-time itself? This theory sits at the crossroads of physics and philosophy, challenging our understanding of both. It suggests that space-time might not be a passive backdrop to the universe, but an active participant shaped by the quantum behaviors of conscious beings. Imagine a world where our thoughts, on some level, influence the flow of time or the curvature of space. It's a concept that blurs the line between science and metaphysics, pushing us to rethink what it means to exist in the universe. But how does this idea connect to the broader concept of space-time as a network? If consciousness interacts with space-time on a quantum level, then space-time itself could be seen as a vast, interconnected web, a network where thoughts and particles alike play a role in shaping reality. This perspective ties together the physical and the metaphysical, suggesting that the universe is not just a collection of objects, but a dynamic system where mind and matter are inseparable. And if we can learn to navigate this network, the possibilities for hacking space-time could be limitless. What if space-time isn't a smooth, continuous fabric, but instead a vast, interconnected network? This is the bold idea behind the 27th theory, space-time as a network. Imagine the universe as an intricate web, with nodes representing discrete points and connections acting as the threads that bind them together. These nodes and connections could form the fundamental building blocks of reality itself. It's a concept that draws inspiration from theories like loop quantum gravity, which suggests that space-time might be quantized, broken down into tiny, indivisible units. If this is true, then manipulating these nodes and connections could open up entirely new possibilities for hacking space-time. Think of it like this: if space-time is a network, then altering the connections between nodes could create shortcuts, bypassing the usual constraints of distance and time. Picture a maze where the walls can shift, allowing you to move from one point to another in ways that seem impossible in a rigid, unchanging structure. This idea isn't just science fiction, it's a framework that could redefine our understanding of the universe. By rewiring the connections in this cosmic network, we might one day create new pathways through space or even alter the flow of time itself. But how does this connect to the broader picture? Theories like this don't just challenge our understanding of space-time, they also hint at the symmetries that govern its behavior. Symmetries, in this context, are the underlying rules that dictate how space-time behaves under certain transformations, like rotations or shifts in perspective. If space-time is a network, then these symmetries might emerge from the way nodes and connections are structured. Understanding these relationships could be the key to unlocking new ways to manipulate the fabric of reality. As we explore this idea further, it's worth asking, what would it mean to harness the power of space-time as a network? Could we one day engineer these connections to create faster-than-light travel or even control the flow of time? The possibilities are as vast as the network itself, and they invite us to rethink not just how we see the universe, but how we might one day shape it. Imagine the universe as a grand symphony where every note, every rhythm is dictated by the symmetries of space-time. These symmetries, like the rotational and translational invariances that govern the cosmos, are the invisible rules that keep everything in balance. Rotational symmetry means the laws of physics don't change no matter how you turn or spin your perspective. Translational symmetry ensures that moving from one point in space to another doesn't alter how the universe behaves. These principles are the bedrock of our physical laws, from gravity to electromagnetism. But what if we could bend or even break these symmetries? Could we rewrite the rules of the game? This is where the idea of hacking space-time comes into play. By manipulating these fundamental symmetries, scientists speculate that we might unlock entirely new phenomena. Imagine harnessing energy in ways we've never thought possible, perhaps by creating asymmetrical distortions in space-time that generate power without the need for traditional fuel. Or consider the potential for motion beyond the limits of our current understanding. If we could tweak these symmetries, could we achieve propulsion systems that defy conventional physics, enabling travel across vast cosmic distances in the blink of an eye? These aren't just wild fantasies, they're grounded in the tantalizing possibilities of altering the very fabric of reality. But how could we even begin to approach such a monumental task? One intriguing idea is to treat space-time not just as a physical structure, but as a kind of cosmic code, a set of instructions that dictate how the universe operates. If we could decode this space-time programming, we might find ways to rewrite it, effectively hacking the universe itself. This perspective bridges the gap between physics and information theory, suggesting that the symmetries of space-time are like the algorithms that run the cosmos. By understanding and manipulating these algorithms, we could unlock capabilities that seem almost magical by today's standards. This leads us to an even deeper question. If space-time is a code, what kind of programmer wrote it, and what other secrets might it hold? The symmetries we observe today could be just the beginning, hinting at layers of complexity yet to be uncovered. As we explore these ideas further, we'll dive into the concept of space-time as a programmable entity, examining how this perspective could revolutionize our understanding of the universe and our place within it. What if the fabric of space-time isn't just something we interact with? What if it's something we could rewrite? This is the provocative idea behind the 29th theory, space-time as a code. Imagine the universe not as a vast, unchanging expanse, but as a dynamic system of information, a kind of cosmic software running on the hardware of reality. This concept, rooted in theories like digital physics, suggests that space-time might not be a smooth, continuous fabric, but instead a digital framework made up of discrete units of information. Think of it like the pixels on a screen or the bits in a computer program, tiny building blocks that, when combined, create the world we experience. If space-time is indeed a form of code, then hacking it wouldn't just be about bending or warping it, it would mean reprogramming it. Picture this: just as a coder can alter a program by rewriting its lines, what if we could rewrite the very rules of reality? This idea blurs the line between physics and computer science, suggesting that the universe might operate more like a computational system than a traditional physical one. It's a radical shift in perspective, one that forces us to rethink everything from the nature of gravity to the flow of time itself. But how would this work in practice? Some theorists propose that spacetime's code could be accessed through extreme conditions like near black holes or in the quantum realm, where the rules of classical physics break down. Others suggest that advanced civilizations might one day develop the technology to debug the universe, identifying and fixing errors in the cosmic code. It's a mind-bending idea, but it's not entirely science fiction. After all, we already manipulate information in extraordinary ways, from quantum computing to artificial intelligence. Could hacking space-time be the next frontier? This theory also opens the door to another fascinating possibility. What if space-time isn't just a code but a simulation? If the universe operates like a program, could it be running on some kind of cosmic computer? This idea, often referred to as the simulation hypothesis, suggests that everything we know, stars, planets, even our own thoughts, might be part of an incredibly advanced simulation. It's a concept that ties directly into the idea of space-time as code, and it's one that challenges us to question not just how the universe works, but what it really is. What if everything we perceive as reality, our universe, its laws, even time itself, is nothing more than an incredibly advanced simulation? This is the core of the simulation hypothesis, a theory that has captivated scientists, philosophers, and sci-fi enthusiasts alike. But let's take it a step further. What if space-time, the very fabric of our existence, is part of this simulation? If that's the case, then hacking space-time might not be about bending physical laws, but about understanding and rewriting the code that underpins it all. Imagine space-time as a vast, intricate program running on a cosmic computer. Every event, every particle, and every law of physics could be lines of code in this cosmic software. If we could decode this program, we might unlock the ability to manipulate reality itself. Scientists like Nick Bostrom have suggested that if our universe is a simulation, it's likely designed by an advanced civilization, one that has mastered the art of creating and running such simulations. But here's the kicker. If we're living in a simulation, could we, as part of this system, find a way to access and alter its programming? This idea isn't just philosophical musing. Some researchers have proposed that if space-time is a construct, it might operate like a grid, with each point governed by computational rules. By identifying these rules, we could potentially rewrite them. For example, what if we could change the speed of light or tweak the gravitational constant? Such changes could allow us to create entirely new realities or bypass the limitations of our current universe. It's a mind-bending thought, space-time as a malleable framework waiting to be hacked. But how would we even begin to approach this? One possibility lies in quantum mechanics. If space-time is a simulation, it might function like a quantum computer, processing information at the smallest scales of reality. Quantum computers already manipulate bits of data in ways that defy classical logic, so could space-time itself be a quantum computational system? If so, understanding quantum mechanics might be the key to unlocking the code of the universe. This theory opens up a world of speculative possibilities. Could we one day create our own simulations within the simulation, or even merge our reality with others? While these ideas might sound like science fiction, they force us to rethink our understanding of space-time and its fundamental nature. And as we explore these concepts, we begin to see a fascinating connection: the idea of space-time as a quantum computer, a system that processes information at the very foundation of reality. What if space-time itself were not just a static stage for the universe, but an active, dynamic system, one that processes information like a quantum computer? This is the mind-bending idea behind the 31st theory, space-time as a quantum computer. At the heart of this concept is the notion that the very fabric of reality might be performing calculations at the most fundamental level, encoding and processing information in ways we're only beginning to understand. Think of it like this: in a traditional computer, bits of information are processed in binary zeros and ones, but in a quantum computer, the rules change. Quantum bits or qubits can exist in multiple states at once, thanks to the strange phenomenon of superposition. Now, imagine if space-time itself operated on a similar principle, with every point in the universe acting as a tiny computational node. This could mean that the structure of space-time isn't just a passive backdrop, but an active participant in the universe's operations. What's even more fascinating is how this theory could open the door to manipulating space-time itself. If space-time is computational, could we find a way to hack it? Some scientists speculate that by understanding the algorithms or protocols governing this cosmic computation, we might one day learn to rewire the fabric of reality. Picture being able to adjust the flow of time, alter the curvature of space, or even create entirely new regions of the universe, all by tapping into the underlying computational processes. But how does this connect to space-time as a living entity? If space-time is computational, it begins to resemble something far more dynamic, almost like a living system. Just as a living organism processes information to adapt and evolve, space-time might be doing the same on a universal scale. This idea blurs the line between the physical and the informational, suggesting that the universe itself could be a kind of self-organizing, self-aware entity. As we delve deeper into these ideas, we're not just exploring the nature of reality, we're redefining what it means to interact with it. Could the key to unlocking the universe's secrets lie in understanding its computational nature? And if so, what might that mean for our future? What if space-time isn't just a static stage where the universe unfolds? What if it's alive? That's the audacious idea behind the 30-second theory, a concept that dares to imagine space-time as a living, evolving entity. Picture this: instead of being a rigid, unchanging framework, space-time could grow, adapt, and even respond to its environment, much like a biological organism. This theory draws inspiration from the natural world, using metaphors of life to rethink the very fabric of reality. Proponents of this idea suggest that space-time might have its own metabolism, a dynamic process where it absorbs and processes energy, much like a living cell. If true, hacking space-time wouldn't just be about manipulating equations or exploiting gravitational loopholes. It could mean interacting with it as a living system. Imagine trying to communicate with space-time, triggering changes in its structure or behavior. It's a bold leap, blending the boundaries between physics and biology, and it raises fascinating questions. Could space-time have a form of memory? Could it heal itself after disturbances, like a wound closing? This theory also opens the door to a deeper connection between the cosmos and life itself. If space-time is alive, then everything within it, stars, planets, and even us, might be part of a larger, interconnected system. It's a concept that feels almost poetic, suggesting that the universe isn't just a cold, mechanical machine, but a living, breathing entity. As we explore these ideas, they naturally lead us to another intriguing concept: space-time as a canvas. If space-time is alive, then it's not just a backdrop, it's a medium that can be shaped, painted, and perhaps even reimagined. And that's where the real possibilities begin to unfold. What if the universe itself is a masterpiece in progress, and space-time is its canvas? This is the heart of the 33rd theory, the idea that space-time might be less like a rigid structure and more like a dynamic, ever-evolving painting. At its core, this theory suggests that the laws of physics, gravity, motion, even time itself, are not set in stone but are instead painted by underlying quantum processes. Think of it like this: just as an artist uses brushstrokes to create a scene, the universe might be shaped by the tiniest, most fundamental interactions happening at the quantum level. Now, if space-time is a canvas, what would it mean to hack it? Imagine being able to step into the role of the artist, tweaking the quantum processes that define reality. By altering these fundamental properties, we could potentially reshape the very fabric of existence. This isn't just about bending space-time or creating wormholes, though those are fascinating possibilities. It's about something even more profound: the ability to rewrite the rules of reality itself. Some scientists speculate that if we could master this kind of quantum manipulation, we might even be able to create entirely new universes, each with its own unique set of physical laws. Picture a multiverse where every universe is a different painting, each one governed by its own palette of forces and constants. The implications are staggering, opening up possibilities that sound more like science fiction than science, yet they're grounded in serious theoretical exploration. But here's where things get even more intriguing. If space-time is a canvas, could it also be something else? Could it be a game? In this view, the universe might operate like an incredibly complex simulation, where the rules of physics are the rules of the game. And just as a player can find hidden mechanics or exploits in a video game, perhaps we could discover ways to hack the universe itself. This leads us to the next big idea. What if space-time isn't just a canvas or a game, but both at the same time? A place where creativity and logic intertwine, offering endless opportunities to explore, manipulate, and maybe even rewrite the code of existence. What if the universe itself were a game, a vast, intricate playground with rules that aren't as fixed as we think? This is the bold idea behind the 34th theory, space-time as a game. Imagine the fabric of reality not as an unchangeable structure, but as a dynamic system governed by rules that could be bent, rewritten, or even broken. It's a concept that draws inspiration from fields like game theory, which studies strategic decision-making, and computational physics, which models the universe as a kind of cosmic algorithm. Together, these ideas suggest that space-time might operate like a game, with its own set of mechanics that could, in theory, be hacked. At the heart of this theory is the notion that the laws of physics might not be as immutable as they seem. Just as a game can have its rules tweaked by a clever player, the universe might allow for certain loopholes or manipulations. For example, in game theory, players can find ways to exploit the system to their advantage. Could the same principles apply to space-time? Some scientists speculate that if we understand the rules deeply enough, we might one day find ways to alter them, perhaps by creating wormholes, bending light, or even manipulating the flow of time itself. This idea isn't just science fiction. Computational physics has already begun to model the universe as a kind of simulation, where space-time emerges from underlying algorithms. If that's the case, then understanding those algorithms could be the key to unlocking new ways to interact with reality. Think of it like learning the code behind a video game. Once you know how it works, you can start to modify it, creating shortcuts, glitches, or entirely new possibilities. But what would it mean to hack space-time? Picture this. If we could change the rules of the game, we might be able to travel faster than light, reverse entropy, or even create entirely new dimensions. These aren't just wild fantasies, they're potential outcomes if the universe truly operates like a game. And while it's still speculative, this theory opens up a fascinating new way to think about our place in the cosmos. Instead of being passive observers, we might one day become active participants, shaping reality itself. As we consider these mind-bending possibilities, it's worth reflecting on what they mean for our understanding of reality. If space-time is a game, then the rules we've always taken for granted might be more flexible than we ever imagined. This theory challenges us to think bigger, to question the very foundations of existence, and to explore what it truly means to hack the universe. And as we move into the final section, we'll take a step back to consider the broader implications of all these theories, not just for science, but for how we see ourselves in the grand scheme of things. As we reach the end of this journey through the mind-bending possibilities of hacking space-time, let's take a moment to reflect on the incredible theories we've explored. From the tantalizing idea of wormholes, cosmic shortcuts that could connect distant parts of the universe, to the mysterious phenomenon of quantum entanglement, where particles communicate instantaneously across vast distances, the universe seems to hold secrets far beyond our everyday understanding. Then there's the simulation hypothesis, which suggests that our reality might be an intricately crafted program, and the notion that space-time itself could be a kind of game, with rules waiting to be decoded and manipulated. Each of these theories challenges us to rethink not just the fabric of the cosmos, but our very place within it. What makes these ideas so profound is their ability to stretch the boundaries of what we think is possible. If space-time can be hacked, what would that mean for humanity? Could we one day unlock the ability to travel across galaxies in an instant, or even rewrite the rules of reality itself? These questions don't just belong to scientists, they're invitations for all of us to wonder, to question, and to imagine. While we may not have definitive answers yet, the pursuit of these ideas pushes us closer to understanding the true nature of the universe and perhaps our role within it. But the conversation doesn't end here. These theories are just the beginning of a much larger exploration, and we'd love to hear your thoughts. What do you think about the possibility of hacking space-time? Do you believe wormholes could exist, or is the simulation hypothesis closer to the truth? Share your ideas in the comments below. Let's keep the discussion going and see where it takes us. If you've enjoyed diving into these cosmic mysteries with us, don't forget to subscribe and hit that notification bell. There's so much more to explore, from the cutting-edge science of black holes to the mind-blowing possibilities of alternate dimensions. Together, let's continue unraveling the secrets of space-time and uncovering the wonders of the universe. Thanks for joining us on this journey. See you in the next video.